we take a break. If enough people want to stay, yeah, I will continue, of course, it's happy to continue. Otherwise, we call the day at midnight, okay?
But really, it's not. I mean, it's not a death march to the end of the subject. Okay, we can start, and please do interrupt with lots of questions. Okay, this is only.
Okay, let's start.
All right, let's start. Okie dokie. So let's now talk about gluon amplitudes and n equals 4 super-Yang mills. And we're going to do a couple of things. So now we're going to talk about the kinematic space again. So we always begin by thinking about kinematic space. And now, most naively, the kinematic space is I have the momenta that are lambda, lambda tildes. So A runs from 1 to n. And if we're doing n equals 4 super-Yang mills, the amplitudes are a function of the lambda tilde, as well as these Grassmann variables. Did Jake talk about these Grassmann variables? Okay. So there are these Grassmann variables that sort of unify all the helicities into a Grassmann coherent state. Okay. So, all right. Okay. Now, already there's kind of there's a very early story here that I think Jake probably talked about, which is that we can think about, so there's a story of the positive Grassmannian. But here's a motivation for where the positive, at least where the Grassmannian comes from, which is just thinking about the data. So let's say you give me the data for lambda 1 through lambda n. Okay, so each one of these is a 2 vector. So that would literally be like A1, B1, A2, B2, up to AN, BN. Okay, and that's the most obvious way we think about the external data as n 2 vectors, right? But we can also think about this data as 2 n vectors. We can think about it as 2 row vectors rather than n column vectors. And if we do that, so let's say here is one giant vector A, another giant vector B in this n-dimensional space. Okay? So that's another way of specifying that data of lambda. Just these 2 giant vectors. Now let's say you go to a different Lorentz frame. Lorentz transformations act like SL2, right, on lambda and lambda tilde. So in a different Lorentz frame, I'll have some different vector, A prime and B prime. But there's something which is common. What is invariant? What's invariant is the 2-plane that's spanned by A and B. Right? Because in the new frame, the A prime and B prime are just some linear combination of A and B. So while the vectors change, the 2-plane that's spanned by them does not change. And so that's the Lorentz invariant information about the lambdas, is just specifying this 2-plane in n dimensions. So that's already pretty cool. That's why Grassmannians have anything to do with anything. Okay? The external data of lambdas is given by a 2-plane in n dimensions. Where is this business about planes coming from? Why do we talk about these vector spaces, planes, Grassmannians, all these things of linear algebra, vector spaces? Where is all this coming from? It's because of this slightly magical fact that the space-time symmetries in 4 dimensions are linear transformations. Okay? That the Lorentz symmetry is SL2 cross SL2. And that, in fact, if we generalize to the conformal symmetry, is SL4. There are all these SLs, right? There are all these linear transformations are the sort of clue that there is some underlying vector space linear algebra type structure going on. Okay? Anyway, I think Jake probably talked about this. So that's the picture for the lambdas, and there's a similar picture for the lambda tildes. So here's lambda. Here's lambda tilde. So here's lambda as a two-plane. Lambda tilde as a two-plane. And I've drawn them this way because, in fact, they have to be orthogonal to each other. And why do they have to be orthogonal? That's momentum conservation. Momentum conservation is a statement of the sum over A, lambda tilde A, alpha alpha dot is equal to 0. That means if I take any vector in this space, it's orthogonal to any vector in that space. Is that clear? Okay. So that's already kind of cool. That, yes?
So the Grassmannian picture you're running out by GL, is that you pull off a factor of the
this is actually important. This is actually important. Here, I'm not modding out by anything yet. Okay? I'm just saying that, in other words, we don't ordinarily mod out by Lorentz transformations. Okay? I'm just making a statement that, that the Lorentz invariant data of the problem is this two-plane. I have a two-plane and another two-plane. Okay. So, all right. Now, and part of the early motivation for the Grassmannian was this looks like a slightly complicated quadratic constraint, but let me draw it like this now. I've just collapsed the picture. So this is a two-plane, this is another two-plane, and this should be orthogonal. But instead of directly saying that lambda should be orthogonal to lambda tilde, you introduce another actor in the game. And the other actor is a k-plane. You say there's a k-plane C. Okay, there's a k-plane CK. And then you ask that CK should contain lambda, and that CK should be orthogonal to lambda tilde. Did Jake talk about this? Okay, excellent. Good, good. All right. And that, of course, enforces momentum conservation. And what you're then supposed to do is say, okay, so I plonk down some delta function. I'm being a little impressionistic here because I'm sure Jake talked about it. You impose a delta function that says C contains lambda, some delta function that says C is orthogonal to lambda tilde. Supersymmetrically, there's some delta function that says C is also orthogonal to eta tilde. There's various motivations to say where that comes from. Okay? But then you have to integrate over the space of these planes. So you have to integrate over the space of k-planes in n dimensions. I think of a k-plane in n dimension as a k by n matrix modulo GLK. And the final thing left to do is to talk about the measure. And then there is this beautiful form that involves all the cyclic minors of the k by n matrix downstairs. Did Jake talk about this formula? Okay, excellent. But all we need to know, we don't need to know the great details now. All we need to know from here is that there's an integral over the space of k-planes in n dimensions. With this, so there's this action happening inside the Grassmannian, and the external data is a sort of window in just from this requirement that C contains lambda and is orthogonal to lambda tilde. All right? Okay, good. All right, and that's one beginning, and we can go on from there to talk about many other things. But I want to take a little detour. Maybe now I'll try this, because I want to leave this up. Oops. That's a little slow. Are you sure this is a better idea? Yeah? God, I'm so bored already. Nobody has complained? All right, let me register my complaint then. When you told me, I thought it was some really, shoo, shoo, it'll be so. No, you sit there, you wait for ages, you forget what you wanted to say. You wonder if your pizza is still warm. You wonder whether you can make any new mob connections importing communist Coke into the U.S. Is there a Czech mob? Are you allowed to say? You didn't say anything. There is a Czech mob. the Yara father. All right, very good. What was I saying? All right, yeah. Separately from here, for the moment, there's a picture of momentum twisters. How many of you know what momentum twisters are? Put up your hand. Okay, about half of you. So it's very simple. So we'll do it in a self-contained way. Okay. The motivation here is to make our kinematic space as simple as we possibly can. All right. Maybe I should have said this to begin with. See, the ordinary way of thinking about kinematic space is n null momenta that add up to 0. Right. So that's already very, very constrained because each momentum has got to satisfy p squared equals 0. So that's constrained, and they have to add up to 0. That is constrained. When we say p equals lambda lambda tilde, we at least trivialize the p squared equals 0 constraint, and the remaining the residual redundancy is just the little group, so it's good, right? But we're still left with imposing the sum of lambda lambda tilde equals 0, which is this ugly quadratic constraint. And I don't know if any of you guys, just as a practical matter, if you play with amplitudes, do you have somewhere on your laptops like data, scattering data? Someone at some point in your life, you must have made 7 momenta that add up to 0 that are null, and it's a pain in the ass because there's some final formula with a square root in it somewhere, and it's really horrible, right? So you always have to do that. Oh, you make the last one and you solve for them, and there's a square root. It's just disgusting. That can't be that can't be what anything grand is written in terms of. So this is a step in the right direction, upstairs, right? Because we're also kind of trivializing momentum conservation, but in this auxiliary way, adding these extra k-planes and so on, right? That's the... Now, there's something else that we can do, much more direct, and in a moment, we'll see how these things are connected to each other. In fact, if we never knew about momentum twisters and all the things that I'm about to tell you, we would discover them starting from this picture upstairs. Just on the nose, just doing the obvious thing proceeding from the picture upstairs, we would discover them. But I want to tell you the sort of most direct way of discovering them, which is to come back and draw our famous picture of the sort of null polygon. Okay. Now these are really 4 vectors. We're in 4 dimensions. So we have a bunch of momenta that add up to 0. Okay. But each p is null, each p squared equals 0, so each p is lambda lambda tilde. But we still have this constraint. Okay. But when we draw this picture, instead, so we have this. When we draw this picture instead, we're saying that each p is the difference between the coordinates of the 2 vertices, right? So we label the vertices x1, x2, x3, and so on. So this is this sort of dual x space. X here has coordinates of momentum. Okay, so these x is not the ordinary space-time. The x is units of momentum. So this is the dual coordinate space, or the momentum coordinate space. I don't know what you want to call it. I forget what we call it, the dual space. Okay. But the problem now is we have to enforce that the x's are null separated from each other. Okay. All right, and so now comes the first sort of foray into twistor geometry. And there's a huge amount to say about twistors, but we need a tiny amount for this. And for essentially anything that you work with momentum twistors and all this stuff, you need nothing more than the next 10 minutes I'm about to tell you. Okay, so this is not a scary thing. You don't have to like start knowing about, you know, O plus minus, cohomology, check, blah, dolbo, blah, nothing. None of it is as super irrelevant as possible, okay, to this subject. I'm not saying it's entirely super irrelevant. It's relevant to other things, but not to this. This is super basic kinematics. To begin with, we're going to ask a really simple question. What does a null ray in space-time look like? And now we're going to imagine, by null ray, I really mean this. Everything here is complex. Okay? Everything is totally complex. So what I really mean is a linear equation, right? Such that I want to look at the set of all x's that satisfy a linear equation, all x's on some kind of plane, such that x1 minus x2 squared is equal to 0. Right? And x1 and x2, there's a linear space such that any pair of x's on this plane are null separated from each other. Now, this means that x1 minus x2, if I think of it as a 2 by 2 matrix, alpha alpha dot, well, it has a vanishing eigenvector, right? So there is some lambda for which this is true. Or the alpha dot, but let's say I'm doing it with lambda. And this in turn means that all of the x's on this line, it's a linear equation, so all the x's on this line satisfy, on this ray, satisfy that x lambda, x alpha alpha dot, lambda alpha equals mu alpha dot for some mu. Okay? And that's the Penrose incidence condition. So this is a linear equation in X space, right? And this linear equation in X space, all the x's that satisfy this equation are null separated from each other. Is that clear? Now, if you want to think about this as a real equation, we want to think about lambda and lambda tilde and mu as real, everything is real, then you've probably discussed that when the lambda and lambda tilde are real is when we're in 2,2 signature, not in 3,1 signature. In 3,1 signature, the lambda tilde should be the complex conjugate of lambda star. Well, lambda tilde should be lambda star, plus or minus lambda star. In 2,2 signature, lambda and lambda tilde are random, independent, real variables. So what is this? This is two equations, right, on a four-dimensional space of x's. There's two components, right, for the alpha equals 1 and alpha equals 2 components. So this is a two-plane in 4 dimensions. Is that clear? And that's what a null ray looks like in 2,2 signature. Okay? A null ray is a two-plane in 4 dimensions. There's another kind of two-plane in 4 dimensions with the alpha dot rather than the alpha. Okay, so there's two kinds of two-plane in 4 dimensions where the things are null separated from each other. Is that clear? Okay. All right. But anyway, if you're doing everything in the complex, you never have to worry about these things so much. Now, a cool thing here. So I'm going to draw the null ray like a line, but remember. In Minkowski space, it's a plane. It's a two-plane in 4 dimensions in the complex, or a complex two-plane in 4 dimensions. But here I'm going to draw it as a null ray in space-time. So this is a picture of space-time. These are all the x's. These are all the x's, and they're just span this. They span this ray. So it looks like the x's are characterized by a lambda and a mu. So if you give me, I'm going to just group the lambda and the mu in a variable z. Since I'm Canadian, it's z. Okay. So it looks like if you give me z, which is a 4 vector, that specifies a null ray. Okay, but not quite, because clearly if I take this equation and I multiply everything by a factor of 2 or by any factor of t, I'm not going to change the x's that satisfy this equation. Okay? So the z's are equivalent to t times z. In other words, if I multiply everything by t, the null ray that they correspond to is exactly the same. Is that clear? So this is our most basic correspondence between a null ray in space-time on the one hand, and there's this now point z equals lambda mu up to rescaling. And this is twistor space, TS, and it's a 3-dimensional projective space, right? 4 vectors up to rescaling, so it's a 3-dimensional projective space. Okay, so far so good? All right. So that's the first part of the correspondence. The second part of the correspondence is what happens if we have 2 of these null rays in space-time? Let's say I have 2 of these null rays, x1 and x2. So I have x1, or let's call them xa and xb. xa lambda equals I have x lambda a equals mu a. And I can ask, is there a point in common between xa, between the null ray for A and the null ray for B? Now, just by counting, there should be 1 point in common, right? Because there are 2 equations that from A for x, and another 2 equations from B for x. So that's 4 equations for the 4 components of x. That's why you should expect that there is 1 point in common between 2 planes. You might find this maybe so hard to visualize, but two planes in 4 dimensions should intersect at a point generically. Okay? And it's for this reason, right? That the equation for one plane is 2 equations, the equation for the other plane is 2 equations, so the total number of equations is equal to the number of unknowns. Okay, so that's what we can ask. Is there a point in common? Is there a point in common between these 2 null rays? So let's look for it. It should be a point x that's both on this line as well as on this line. Okay? And we can very easily solve for this. And it's x alpha alpha dot is mu a alpha dot lambda b. I might have the overall sign wrong. Minus mu b lambda dot alpha lambda a divided by lambda b lambda a. Okay? I think it should be sort of more or less clear, right? If you just multiply the top equation by mu tilde b, by mu b, and the bottom equation by mu a, and you subtract them, then this is what you get. Okay? So indeed, if there is a point where 2 null rays intersect, right? We found the point. So we have a second part of the correspondence now. Let me draw this a little more neatly. So down here we have space-time, and we have a null ray in space-time, and here we have twistor space, which is a P3, and here we had a point. But now, if you give me 2 points in twistor space, A and B, this seems to give me a point in space-time, X, labeled by A and B. Right? Except it's still not just A and B separately. Why not? Because if I take these 2 equations, I can take any linear combination of these 2 equations that I want. And that'll still give me exactly the same solution, X. So that means that I can replace ZA and ZB by any linear combination of ZA and ZB that I like. And that will give me exactly the same point. So what do all linear combinations of ZA and ZB look like over here? Like here is 1 times ZA plus 0 times ZB. This is 1 times ZB plus 0 times ZA. What's something in between? Is something there? A third, 2/3, right? Every linear combination will give me points on the line that connects A and B. That's what defines the line. All possible linear combinations of A and B. So we learned something a little more interesting, that it's kind of interesting that a line or a null ray in space-time is a point in twistor space, but a line in twistor space is a point in space-time. And we can label, if I want, just to remember, I can label this by giving an A and a B on the line, but I always have to remember that the line only occurs in the combination AB, right? I mean, I can do it, take any linear combination of A and B that I like. AB is just like a marker for just some way of labeling 2 points on the line. Okay. Now, the most beautiful thing about twistors is that they make the action of conformal symmetry obvious. And, you know, the exciting part of conformal invariance is not scale invariance. Scale invariance any idiot could think of, okay? The exciting part of conformal symmetry are the inversions. The inversions are the thing which are kind of a little mind-blowing, right? And in fact, you know, since most of you are probably physics enthusiasts from a young age, you know, everyone knows that you can solve the problem of what does the electric field look like outside a conductor, right? And you know how to solve this problem, that we have this picture with the electric field lines going like this, but how do we solve it? We solve it by putting an image charge on the other side, right? So this is very easy, and you can solve it. But then you see at some point a teacher kind of amazes you that you can do the same thing if you have a charge outside a grounded sphere, a spherical conductor. And the amazing thing is that if you're out a distance r here with some charge q, there is some intelligently chosen q prime that you could put here at, if this radius is little r, at r squared over capital R, which also makes this an equipotential surface, right? So it's possible to solve the spherical problem with the method of images too. But it's because of a little miracle that you look, then you put with the right value of the charge that you can make it an equipotential surface, okay? And that miracle is exactly the symmetry of massless Laplace equation, not even all electrodynamics, under inversions. That's the conformal symmetry. And that's the hallmark, that it takes something very far away and it replaces it by something very close by. Inversions is the exciting part of the conformal symmetry. Now, as you also probably know, if we think the infinitesimal version of inversions is the special conformal transformations, and it's not really the infinitesimal version of inversions, but the infinitesimal part of the conformal group. The exciting part is the special conformal transformations, and what are they? It's what you get when you start somewhere, you invert, big change, you make a small translation, and then you invert back. Okay? And that process now makes a small change compared to where you started, and that's what the special conformal transformations are. All right? But if we look in total at all the symmetries of the conformal group, there's things that look like translations, ddx. There are things that look like Lorentz and rotations, x ddx. And then there's conformal that looks like xx ddx. I'm not being careful with the, all the indices, okay? But that's already slightly unsatisfying, that the space-time symmetries all of these guys get unified into a nice group together, and the big group then on a different footing. But we're putting them on quite a different footing when we represent the asymmetries in this way. So this shows that the choice of kind of working with space-time coordinates is obscuring the action of the, is kind of obscuring the unity of the conformal group. Makes some generators look different than others. Okay? All right, well, that's the beauty of twistor variables. The beauty of twistor variables, if I say this another way, if I take two random points, I don't know, x and y in space-time, then if I look at the distance between them, x minus y squared, under inversions, x minus y squared goes to x minus y squared over x squared y squared. In other words, if I send x to x mu over x squared and y mu to y mu over y squared, then under inversions, of course, the distance isn't invariant. Duh, right? So clearly, the distance being non-zero is not a conformally invariant notion, not even a scale invariant notion, definitely not a conformally invariant notion. But what's cool is that if x and y are null separated, then null separation is a conformally invariant notion. Okay, if they're null separated before inversions, they're null separated after inversions. And that's why it's a good idea to look at sort of null rays in space-time. Apart from their intrinsic interest, they're also conformally invariant things. Okay, one null ray in space-time under conformal transformations transforms to another null ray in space-time. And we can actually see the action of the full conformal group very nicely on this formula, x lambda equals mu. Okay? What happens if I do the SL2 cross SL2 of Lorentz is obvious. There's the SL2 that acts on the alpha dot and on the alpha index. But under translations, if x goes to x plus d, well, this equation just goes into itself where I shift mu goes to mu minus d lambda. Okay? So in other words, translations just act like a linear transformation on lambda and mu. So if we look here on lambda and mu, I forget, maybe put mu upstairs. I forget who we put upstairs. Anyway, there is a 2x2 linear transformations up there and 2x2 linear transformations down there. And we also have a transformation where lambda is translated by mu. Right? So that's down here, like D. Right? Well, so there's something little left up there. Those are the special conformal transformations. But it's actually super easy to see that just directly at the level of the inversions. Because if I take this equation, x lambda equals mu, then lambda is equal to x inverse mu. Right? Now, under inversions, in terms of the alpha alpha dot variables, x is literally going to the inverse matrix x inverse. And so, under inversions, we just interchange lambda and mu. The world's simplest linear transformation, just interchanging lambda and mu. So we see that all of the conformal group is just 4x4 linear transformations on Z, right? That's the glory of twistor variables, is that they manifest as simply as possible the action of space-time symmetries But the beautiful thing is that the space-time symmetries do not act mostly on space-time points, but they act most simply on rays through space-time. That's really remarkable. Okay, so we have so the conformal group is Z goes to LZ, where L is just any 4x4 matrix. Okay, and if there's an overall factor GL4, that's just part of the little group. Okay, so we can just take this and think of it as part of the rest of it as part of the conformal group. All right. Okay, so now this also means that since this is the symmetry, the only invariant tensor that we have is epsilon ijkl. Is the only invariant tensor. So there's no metric, there's no distance, nothing like that, okay? All we have we have points in P3, these are these twistors, or maybe you have lines in P3 that correspond to points in space-time. But there's nothing we can do, there's no dot product, nothing we can do. The only thing we can do is take 4 of these Zs and put them together with an epsilon symbol. And whenever I do that, I'll just write it as a bracket. Everywhere there's a bracket, something like this, it means that they're contracted together with an epsilon symbol. All of geometry is projective geometry, and if we had 5 more hours, we would do a projective geometry boot camp, but we're not going to do that. But you don't really need to practice to know a whole heck of a lot, other than this very important thing, these are the only invariants. So let's do like one example. Like let's say I have a point in space-time that's associated with this line AB. Okay, so this is a picture in P3 now. This is a picture in twistor space. And I have this line AB. So that's one point in space-time. I'll call this the point XAB to remind myself it came from AB. And then I have another line here, CD. And this is some other point here, XCD. And remember, this only depends on the line, not on the individual points. This only depends on CD, not the individual points. What can these two lines look like? Now, if you want to visualize things in projective space, it's really simple. Just visualize them in ordinary 3 space. There's nothing special about the projectiveness. All the projectiveness does is make it so that you don't have to worry about whether things are parallel or not. You can always imagine that lines and everything are in generic position, and that lines intersect at points in 2 dimensions and so on. There's nothing special with parallelism. And infinity is treated on an equal footing as everything else. But precisely because of that, it means that if you're just thinking about generic configurations, for your visual imagination, just visualize them in 3 space directly. Nothing will go wrong, okay? So that's what you should do. Okay, so what happens if I have 2 generic lines in 3 space? Is there anything special about the relation that I can say? Let's say they're like that. Anything? No. What if they're like that? Ooh, they're so close. Nah. So close means nothing, okay? Okay, you can do an SL4 transformation to put them anywhere. So, okay, so the only thing that's meaningful, what about that? No, the only thing that's meaningful is do they intersect or not? That's it. I love it. It's like super, super hardcore. There's no forgiveness at all, right? Right? So if the lines intersect, that's meaningful, right? That means that's something special. That's a conformally invariant statement. So what does it mean that the lines intersect? It means that this bracket A, B, C, D is equal to 0. Because, for example, that means that if they intersect, it means that A, B, C, and D are actually in a plane with each other, on a 2-dimensional plane. And that means that I can write A as a linear combination of B, C, and D. And that means that this bracket will vanish, right? Okay, yes?
Is that a statement of the Grassmann-Cayley algebra?
Probably. If I knew what it was, I would probably agree with you. It sounds right, yeah. There are definitely the correct names that should go together. But it might be more fancy. What you're saying might be more fancy. Yeah. Okay. Okay. All right. So now, and what does this mean back in space-time? It means that the points are null separated. Now, in fact, there's a very cool formula. If I go back to the formula for x minus y squared, you can actually, remember, I gave you a formula for x is mu a lambda b minus mu b lambda a, etc., right? Over lambda a lambda b. And similarly, there's a similar, this would be x for ab and x for cd. There would be the similar formula for it. And here's an exercise for you. I want you to just work out what is x minus y squared. If you work out x minus y squared, you find the following beautiful thing. It's actually a, b, c, d divided by lambda a, lambda b, lambda c, lambda d. Okay, so that's the formula for the distance squared between 2 points. And you see the numerator only has a 4 bracket in it, so that's invariant under SL4. The denominator is not. It involves something that just contracts the upper 2 components of Z. So you can introduce something that's sometimes called an infinity twister, which is this sort of 2x2 matrix that has an antisymmetric block here and zeros everywhere else, so that lambda A, lambda B, you can just, I mean, this is just to write this as ZA, ZB, I, contracting these indices together. Okay? So that makes it clear that it is possible to have a good notion of distance and so on, ordinary Poincare notions, but x minus y squared involves now a, b, c, d, but there's this thing that's not invariant under conformal transformation, this infinity twister. And notice that this I is exactly something, I can think of it, you see, I also should have said, like, how can I think, if I give you ZA, I, and ZB, J, right? So the I runs from 1 to 4. Well, if I take the antisymmetric combination of these guys, ZA, J, ZB, I, this is a, what is this? This is some antisymmetric 4x4 matrix, right? But it has rank 1, because it's just made out of this one linear combination, so its determinant vanishes. Well, that's exactly what this guy is. That's exactly what this infinity twister is. It's an antisymmetric 4x4 matrix of rank 1. So you can actually think of this I as another line, just some fixed line in P3. Right? So imagine there's A, B, and C, D, and there's a sort of fixed line sitting there dumbly all along, I. Okay? Now, this is just like the symmetry breaking, the Higgs mechanism, all that, well, that's a very, very loose analogy, but the most trivial aspect of the Higgs mechanism. But I have this big SL4 symmetry. If I declare there's this fixed line, well, there's only some subgroup of the SL4 that will preserve that line. And that subgroup is exactly Poincare. Okay? And here's a way of thinking about it. What is this fixed line in P3 back in space-time? Just some fixed point. Right? And this is what we conventionally call the point at infinity. That's why it's called the infinity twister. Okay? So if there's a special point at infinity, well, clearly you don't have inversions, right? The whole point of inversions is that close and far are not distinct from each other. If you say there's a marked point at infinity, that's definitely going to break inversions. And it'll break you down to Poincare. Okay? So this is a sort of full relationship. And this is why these twisters are really useful even when you have only Poincare symmetry, because it's a very easy way of keeping track of infinity. Okay, it's a very easy way of keeping track of, and you know, when you do loop integrals, loop integrands, and so on, it's a very nice way of sort of seeing, instead of worrying about how L is going to infinity and so on. It's a very clean way of characterizing what is going on at infinity. All right, so this is sort of pure kinematics so far. So the most general Poincare invariant theory you can think of as points in space-time are lines in P3. If there's a special line at infinity, then we're down to Poincare. If not, we have full conformal. Okay, yes? Yes. Oh, no, good, excellent. Yeah, so I was just about to say that. This conformal invariance that we're talking about has nothing on the face of it to do with the conformal invariance of the space-time, ordinary space-time. This is some conformal invariance in this dual space-time. All we know at the moment is that simply the kinematics of massless particles has conformal invariance in it. Okay, simply because having n particles that are null, well, we know that nullness is a conformally invariant concept. But we have no idea whatsoever if dynamics does or doesn't have any kind of conformal symmetry. If it doesn't, then we'd see it, that this infinity twister would show up everywhere. Okay? But absolutely, this is not this is the dual conformal invariance, the conformal invariance in this dual space. Absolutely. If you have momentum twisters are a very useful way of thinking about any massless theory when there's a natural ordering. The ordering is important because we have to draw this polygon to begin with. I haven't gotten to the momentum twisters yet, but there will be. But yeah, let's do that. Let's do that right now. All right. So that's everything on the kinematics. But now let's go back, and now this is the payoff. Let's go back to this picture of the null polygon. And let's draw the picture in space-time first. So you see, I have this point here, and this point, and now the only thing that I'm building the fact that the momenta are going to add up to 0 automatically. The only thing that I need to somehow put in is that this point is null separated from this point, is null separated from this point, and so on. Okay? That's the thing which is not hardwired in yet. We'd like to sort of understand how to make that manifest. But this is a picture in space-time. Now let's draw the corresponding picture in twistor space. So if this point is, let's say, x1, x2, x3, and so on, who is x1 in twistor space? So let's draw a picture in twistor space here. x1 is some line in twistor space, right? Here it's some line in twistor space. So this is a line that corresponds to x1. So I'll just label this line 1. Who is x2? It's some other line in twistor space. But what's the crucial thing? The crucial thing is that these two, x1 and x2, are null separated, which means that these two lines must intersect. Okay, so here's the next line. So this is a line for 2. And it's a 4-dimensional, it's a 3-dimensional picture, right? It's a P3. This is a picture in P3. So a 3-dimensional picture. But of course, I can only draw it 2-dimensionally. And here's the next line, and the next line, the next line, the next line, the next line. Okay? So instead of a picture of a null polygon, we just have a picture of a bunch of lines, one intersecting the next. Okay? But here's the spectacular thing. You can completely reconstruct this picture simply by specifying these intersection points. So I don't know, let's call this 1, Z1, Z2, Z3, and so on. In other words, if you just give me n z's in P3, n points in P3, just give me n points. So let's do it backwards. Give me n points in P3 to begin with. 1, 2, 3, 4, 5, 6. Okay? If there was no ordering, there's no natural way to build points in space-time out of these guys. I just have n points. But since there's an ordering, then there's a natural set of lines to draw. I'll draw the line 1, 2, and then 2, 3, and then 3, 4, and then 4, 5, and 5, 6, and 6, 1. And these will correspond to points in space-time that are a null 6-gon. Is that clear? And this is really beautiful because now the z's are completely unconstrained. There's no more constraints. We've managed finally to parameterize the scattering data in terms of completely unconstrained variables. Okay, and if you give me these ZA, I, which are lambda A and mu A, I keep forgetting who's upstairs and downstairs, then this is an exercise that I'll leave for you to do. You can, from these z's, you can work out what are the x's that correspond to Z1, Z2, Z2, Z3, and so on. Then you could look at the difference between two consecutive x's. That's guaranteed to be null, so you should be able to write it as lambda, lambda tilde. And so you should be able to have a formula for what are the lambdas and the lambda tildes that you get in terms of these lambdas and mu's. And of course, the momenta are going to be lambda, lambda tilde, where the lambdas are the same as those lambdas, but the lambda tildes are the following cool formula. The lambda tilde A is lambda A minus 1, lambda A, mu A plus 1, plus cyclic. All divided by lambda A minus 1, lambda A, lambda A, lambda A plus 1. And the final exercise is that you can show that if no matter how the lambdas and lambda, for totally unconstrained lambdas and mu's, the lambda and lambda tilde that you define in this way will satisfy momentum conservation. Okay? And that will be a consequence of the Schouten identity. As everything is that involves manipulations with these little two vectors. All right, there was a question. Yes? Not as usefully, no. Yeah, it certainly is not a general dimensional phenomenon. Twistors are still useful in 6 dimensions to some extent. So there's something special in 3, 4, 6, and 10 dimensions. But it's not remotely as useful as this. Right. Okay, so the most practical thing that we've discovered then is that the scattering data is can be completely given by n 4 vectors. It's ironic. We do all this song and dance. We start with n 4 vectors, except these n 4 vectors satisfy p squared equals 0. And the momenta add up to 0. Now we've replaced them with n totally unconstrained 4 vectors, except each 4 vector has a rescaling invariance. That's a little group. Okay? And I'll leave it for you to puzzle out a little. What happened? I mean, what happened to the sort of 4 extra degrees of freedom? Right? I mean, we sort of lost momentum conservation. Like what, we thought we had like 4n variables. and then maybe n on-shell constraints, so that's 3n variables, but where there's 4 constraints for momentum conservation, so there should be 3n minus 4. Well, what happened here? We seem to have like just 3n. Where do the sort of minus 4 go? And the minus 4 is there in that, well, okay, I'll leave it for you to puzzle that out. It's not complicated. Okay. So, so the kinematic data, when we have an ordering, is most conveniently written in terms of these momentum twistor variables. All right. Any questions about that? Now, let me come back to this picture upstairs, since I used this brilliant board to put it up there this whole time. There's a completely different path that you could take that would also arrive you at momentum twistors. So let's go back to this upper picture where we had this, we're integrating over these K, this is going to be very sketchy. But I just want to give you a picture of what is going on. So up in this picture, we're saying that we want to integrate over all K-planes C that contain lambda and are orthogonal to lambda tilde, right? So C is a K-plane in n dimensions, so C is a K by n matrix. I presume Jake explained this to you. Oops. There we go. I want to speak to my eye. There we go. So C is a K by n matrix. And we're supposed to integrate over all C's that contain lambda and are orthogonal to lambda tilde, right? But if you think about it for a sec, that seems like a little bit dumb. Because C is forced to contain lambda, right? Since C is forced to contain lambda, that means it's possible to take some linear combination of the rows of the C matrix, let's say so that the top 2 components are literally lambda. It's like saying this plane contains lambda, so there's a lambda part and there's the rest of it. So it should be possible to kind of write C as C is equal to, and put sort of lambda upstairs manifestly, and then have some kind of C hat matrix downstairs, which would be K minus 2 by n dimensional. So this would be 2, n, and this would be K minus 2. And then you see, so that takes care of the first delta function that C contains lambda. Then the delta function that C is perpendicular to lambda tilde would just be momentum conservation. And the eta tilde part would just be the super momentum conservation. Okay, so why don't we do this? Okay, no problem. You could do this. But the problem is that if you do this, then naively, those minors downstairs, 1, 2, k, 2, 3 to k plus 1, and so on, they would now depend on lambda, right? Because this is a k by k minor. And now the upper 2 components have lambdas in them, so when I take determinants, they will involve little determinants of lambdas, okay? So there's a natural question that you can ask, and actually, if you think more carefully about what it means to put lambda on the top 2 rows, this is all forced on you anyway, okay? But what you really want to do is further do a linear transformation, a GLN linear transformation that rotates the columns that takes that lambda dependence out of those minors, okay? So, and it turns out there is exactly a linear transformation that you can do now rotating the columns together such that after you do that linear transformation, the things downstairs are now some other matrix D, okay? But that the k by k minors upstairs become k minus 2 by k minus 2 minors downstairs multiplied by, so, you know, I have some, let's say lambda 1, lambda 2, up to lambda k, and then something in between here with 2 smaller, okay? So some matrix D, such that this cyclic consecutive minor of the C matrix, this minor, this determinant, becomes lambda 1 lambda k times the determinant of this little D matrix. So determinant of this C becomes just lambda 1 lambda k times the determinant of this D matrix. But this is after this interesting linear transformation. And that interesting linear transformation turns out to be exactly that interesting linear transformation that we just saw that took us between the mu's and the lambda tildes. Okay? Remember, we had this interesting linear transformation between the mu's and the lambda tildes. Such that when the dust settled, so I'm not explaining this in any detail. This is really the sort of beginning of the story, and it's a short argument, but it's a little bit of an argument. But it begins just by trying to put the lambdas upstairs to trivialize momentum conservation. Okay, what you find is that this integral dk and c mod glk over the cyclic minors of C delta, 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 is actually the integral dn times k minus 2. And actually, let me call this original k hat, because I want to save k for what it is afterwards. Okay, so this is going to be k hat. This turns out to be a dkn d over now the k by k minors, cyclic k by k minors, where k is just equal to k hat minus 2. And here we get instead of all these delta functions, we just get delta for k d dot z, d alpha a, z a. So this is the product over all the alphas. So this is a k by n matrix. ZAI and ZAI is equal to lambda a mu a. Up to a factor, and sorry, remember the whole point of this was that it pulled off a delta function of momentum conservation and a delta function, the super delta function. And there's finally a Jacobian factor of all this. It also takes care of all the little group weights. That's just the Park-Taylor factor. Now, you might say, what the heck is this mu? Where did this mu come from? But the point is that this part of the equation is only on the support of these delta functions. And on the support of these delta functions, that's the whole claim, is that this thing is only a function of lambda and lambda tilde. Why is it only a function of lambda and lambda tilde? Because, notice, by construction, manifestly, this expression is invariant under SL4 transformations. But SL4 transformations on the z's. Okay, so this is manifesting this dual conformal invariance in the z space. Okay. All right. So we learned something very interesting. This structure on the Grassmannian, to begin with, is giving us n to the k hat MHV amplitudes. So k hat equals 2 would be MHV. Okay? That would be k equals 0. Now, I don't know how much Jake explained about the Yangian symmetry or even ordinary conformal invariance, but part of the point of these Grassmannian formulas is that they make the action of conformal symmetry totally obvious. Here, it was written in terms of lambdas and lambda tildes. You can actually go to Penrose's twistor space in order to write a formula that looks identical to this, except the z's are not these dual twistors, but are the twistors that are related by a Fourier transformation to lambdas and lambda tildes, let's say Fourier transforming the lambda tildes. Anyway, if you don't know what I'm talking about, it doesn't matter. The point is that there's a trivial way of seeing this formula as manifestly conformally invariant. But we discover that after we pull off this factor that's just the delta function for momentum conservation and supermomentum conservation and the Park-Taylor factor that takes care of weights, the thing that's left over is manifestly a function that's invariant under SL4 transformations. We discover the dual conformal transformations. So we discover both the momentum twisters. I didn't explain exactly the steps, but I can refer you to the papers, which did it. It's a very short argument. But simply by following your geometric nose and trying to make it manifest that lambda fits in the top two rays of C, you go from this formula to this one. And this formula makes conformal symmetry obvious. This formula makes dual conformal symmetry obvious. Right? And that's a remarkable thing about the Grassmannian. It's the only structure we know that makes the conformal and the dual conformal symmetries manifest at the same time. It makes them both obvious. That's the sort of famous Yangian symmetry is sort of made obvious by these arguments. Okay. And that's another path to discover the momentum twisters, even if you didn't know about them ahead of time. All right. Now, with all of that being said, let's now look at the very, very simplest objects that we can get here. The very simplest objects that we could get if k hat is equal to 2. Oh, sorry. And of course, this is part of this general amplitude-Wilson loop duality, is that if we have an amplitude which depends on lambda tilde, and eta tilde, the claim is that it's equal to delta 4 of momentum, delta 8 of Susie, over Park-Taylor times some other, so this is n and k hat, this is r of n and k, that only depends on z's. And the super, and these etas are like the eta tildes are related to the etas the same way the lambda tildes are related to the mu's. Okay, so right. So this is conformally invariant. This is dual conformal invariant. And super for both. And it's this thing which is interpreted as the expectation value of a supersymmetric Wilson loop. Okay? So that's the other part of the basic connection. All right. But what I want to do now is look at the very simplest objects that we get. In this way. So you probably learned from Jake that that BCFW is related to on-shell diagrams and this is related to cells of the Grassmannian or the positive Grassmannian of G k hat n, the thing I'm calling k hat now. And so I want to look at the very simplest, so if k hat equals 2, that's just MHV, and this integral is nothing. This r of n and k equals 0 is just 1. Sorry, the r isn't 1, but the things that we get from the Grassmannian are just 1. So there's nothing to say, or the tree amplitudes are just 1. Or yeah, at least at tree level, these r, n, k equals 0 tree is just 1. So the first interesting case is k hat equals 3 NMHV. And already back in back in the original on-shell diagrams, these are already some kind of juicy looking on-shell diagrams. You have 3 by n matrices, G3n, lots of fun, right? But this case is simple enough that we can really do it by hand if we take it now down to the to this downstairs smaller Grassmannian. So that's k equals 1. Okay, so for k equals 1, our D matrix is just 1 by n. So I can think of it as like little d1 up to little dn. And so what I'm left with is this integral. I apologize for the many d's. Maybe I should call it something else. This little D matrix is, let me call it delta 1 through delta n. Okay. So this is d delta 1 to d delta n. The product over the cyclic minors is just delta 1 through delta n. I'm supposed to mod out by GL k equals 1. And then what I'm left with is just a delta 4 of delta 1 z1 plus delta 2 z2 plus delta n zn times the delta 4 of the eta part. So delta 1 eta 1. This is the SUSY part plus delta 2 eta 2 plus delta n eta n. All right. Now, how are we supposed to interpret this expression? Well, notice that the z's are all 4 vectors. So I can express any 4 vector as a linear combination of 4 vectors. Okay? So if to begin with, I look at what does this look like for n equals 5? That's the sort of smallest interesting case. For n equals 5, remember this would be 5-point NMHV, which is the same as by parity the 5-point MHV. So we expect this should be a really simple case. Okay? But let's see what this formula looks like in this little Grassmannian here. It's like d delta 1 over delta 1 up to d delta 5 over delta 5. And then I have a delta 4 of delta 1 z1 plus dot dot delta 5 z5. And then there's the eta part, delta 4 of eta 1, delta 1, eta 1 plus delta 5, eta 5. Okay, so far so good? Mod GL1. Now let's think about what this mod GL1 means. Mod GL1 means that if I didn't mod by GL1, this expression is invariant into rescaling all the deltas. So that has a spurious infinity just by that dumb fact, right? So modding by GL1 means that really I only care about the ratios of these deltas relative to each other. Or I can use it to, let's say, set delta 5 equal to 1. Any one of them I want equal to 1. Okay, and then I just do the integral of the remaining 4. So far so good? So modding by GL1 turns us into this really is d delta 1 over delta 1 up to d delta 4, delta 4. And then I have a delta 4 of delta 1 z1 plus delta 4 z4 plus z5. And then a delta 4 of the eta part. But this part is just going to come along for the ride. This is the interesting part, because I have 4 integration variables, but I have 4 delta functions here. So I should be able to use it to solve for all of the deltas. And how do I solve it? Well, see, this is exactly what this is telling me. Z5 is equal to negative delta 1 Z1, negative delta Z2, and so on. This is just the expansion of Z5 in terms of Z1 through Z4. Okay, so let's solve. How do I solve for Z5? Minus Z5 is equal to delta 1 Z1 plus delta 2 Z2 plus delta 3 Z3, delta 4 Z4. Well, let's say I want to isolate delta 1. I just take this thing and I take the 4 bracket with 2, 3, 4. Okay? Then here I'll get delta 1, 1, 2, 3, 4, and the rest vanish. Right? So delta 1 is equal to Z2, Z3, Z4, Z5. I got rid of the minus sign by pushing it all the way to the right, over 1, 2, 3, 4. And so on. Okay, so you get delta 2 is equal to Z1, Z3, Z4, Z5 over what did I? Over what? Yeah, all. Sorry. Yeah, over 1, 2, 3, 4. All of them over 1, 2, 3, 4, and so on. Okay. So I solve for all the deltas in this way, and so that's it. So I've solved for all the deltas. So all those deltas occur downstairs here. Okay. And I get them in this SUSY delta upstairs. So the final expression for this object, this is a famous object, it's called an R invariant. And it's labeled by 5 twistors, 1, 2, 3, 4, 5. Sometimes written as a bracket like this, is equal to delta 4 of eta 1, 2, 3, 4, 5 plus cyclic divided by 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 1, 4, 5, 1, 2, 5, 1, 2, 3. Okay? So that's the very simplest object that we can get from the k equals 1, k equals 1, n equals 5, momentum twister Grassmannian. All right? And the claim is that if you took anything upstairs and the k hat equals 3, and you stripped off the delta functions of the Park-Taylor factor, you'd get this guy, right? Now, what about higher n? Now, what happens for higher n is that we're always looking, we have this integral, but we have to interpret the integral as a residue so that we finally get it down to a point where the number of integrations is equal to the number of delta functions. And what that means for higher n is very simple. All I had is delta, this delta 4 of delta 1 z1 plus delta 2 z2 plus dot, 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 dot. We know that if there's a total of 5 things that occur in that delta function, that's enough to lock everyone. Just like we saw in this example, right? So all I have to do, since my little integrals over d delta 1s are just integrals, I can imagine that I just set them as little contour integrals to set the deltas equal to 0. So I set all but 5 of the deltas to 0, and the rest is something, right? The rest is one of the residues of this Grassmannian integral. So that's the most general object that we can get at for k equals 1. Okay, so for k equals 1, the most general object we can get is actually labeled by any 5 guys, I, j, k, l, m, with exactly the same formula. Okay, they don't have to be consecutive. Okay, just any 5 of them. Okay, any questions about that? So we've now encountered what the very simplest NMHV objects look like. All right, and so now we can finally get to some physics after all of this kinematic setup. I forgot, I have to do this. Oops. Oh no, that's wrong. Oh, I see, like that. Which one? This one is down. Oh, but I can't do them simultaneously. I see. Oh, that's really bad. Oh, sorry. I see. All right, well, okay, here. am I doing wrong? Why is this one not going up? That's, huh? Top button. Oh, there we go. No, but it's only going down, it's not going up. Oh, now it's going up. Very good. It wasn't, maybe I wasn't pushing it enough. Oh, it's slow to respond, that's the problem. Ah, I'm the master. That's great. Okay. Yara's too far gone for the reach of justice here to be, all right. So, all right. Yes. Yes.
Is there some kind of physical explanation for what this D4 with the eta variables is imposing that the D8 we already have?
Yeah, absolutely. Yeah, first of all, if you like, this is maybe a little, first at the most basic level, the overall K has got to be 1. It was 3 and it's got to be 1. We only got rid of 2 by taking out the delta 8Q, right? But if you like, this is the delta 8Q was the delta function for ordinary supersymmetry. This is the delta function for the dual supersymmetry. So the dual supertranslations. Okay, so it's not, so it was not taken care of by the first one. And somehow you have to strip off the first delta functions to even define the second one. That's one of the funny, interesting things, right? The amplitudes are in principle defined for any lambda or anything, and we happen to say they have a delta function. But on the support of that delta function, this other asymmetry comes to life. And so, so it's imposing the dual supersymmetry, which is not the same as the original supersymmetry. Just like the full dual conformal symmetry is not the original conformal symmetry. They only overlap on the Lorentz part, but everything else is different. Okay. So I'm now just going to tell you what does k hat equals 3 means k equals 1 tree amplitudes. What do these look like a la BCFW? And the answer is that the endpoint amplitude for k equals 1, after we strip, now that we're in these dual variables, after we strip off the delta functions and the Park-Taylor factor and all that stuff, is actually beautifully written in terms of these R invariants. Well, it had to be because it's written in terms of on-shell diagrams, and all the on-shell diagrams are turn into this, from what I was telling you before, right? But it turns out there's many ways of doing BCFW, but in one of the simplest ways of doing them, it looks like the sum over I less than j, different than j, of 1 I plus 1, j plus 1. Okay, that's funny, interesting structure. So that's funny, 1 and then I plus 1j. You see, the object should be cyclically invariant. The amplitude is cyclically invariant, but we seem to be breaking cyclic symmetry. There's a 1 is special there, okay? And of course, you know that's true of BCFW. In BCFW, you choose the special people to do the recursion, okay? And here, essentially, you just keep choosing the same last guy to be special in doing the recursion. So that's what gives you this very uniform looking formula. Okay, so let's just look at the first interesting example for n equals 6. The amplitude is, just by these rules, is 1, 2, 3, 4, 5. Plus 1, 2, 3, 5, 6, plus 1, 3, 4, 5, 6. So it's a sum of 3 terms. And let's just for a second look at the pole structure that these terms have. So I'm just writing down the poles, right? The poles that this has are Well, it's just the consecutive 4 brackets, right? So the poles this has are 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 1, 4, 5, 1, 2, 5, 1, 2, 3. This 1, 2, 3, 5, 2, 3, 5, 6, 3, 5, 6, 1, 5, 6, 1, 2, 6, 1, 2, 3, 1, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 1, 5, 6, 1, 2, 6, 1, 3, 4. Oops, oh, sorry, what am I doing? 5, 6, 1, 3, 6, 1, 3, 4. Right, so those are, each term has those 5 sets of poles. Now let's back up for a second. What are the poles that the amplitude should be allowed to have? What are the physical poles that the amplitude should have? The physical poles that it should have, if we go back to our our polygon picture, because of the ordering again, as with our earlier isosahedron story, phi cubed story, the poles that the amplitude can have, the only poles can be when the sum of consecutive momenta go on shell, in this case go to 0, which means when xi minus xj squared goes to 0, right? And this means when the 4 bracket zi plus 1, zj plus 1 goes to 0. Okay? So this ii plus 1, jj plus 1 structure, this is a big key. Okay? You see, it's kind of interesting. The amplitude in the end, well, for example, in these formulas, in this Grassmannian formula, what we see are just z's directly. Z's are the natural variables. On the other hand, the points in space-time, in this dual space-time, sorry, are not z's. They're these lines, like ii plus 1. And they have this ii plus 1 structure in it. Okay? So the most 0th order aspect of what kind of theory you're looking for, so let's back up again. Now, in this context, our kinematic space is just the space of n z's. That's it. Right? This is the most satisfying kinematic space you could imagine, right? As we said, it's just the cleanest way of specifying the scattering data for the external problem. It has some structure in it, which is the ordering, and that's there in the problem. Okay, the problem has it. And it's incredible that that one notion of ordering is all it takes for everything else to unravel. Okay, that we just start with n z's. Just with that space, we can do nothing. But the word ordering is the only thing it takes to begin a whole cascade of events that has the word positivity and Grassmannians and blah, 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 and then we're off to the races, okay? But it really just begins with this word ordering. But now we have an interesting question. We're looking for some theory, some structure, something in momentum twistor space. So our space, our kinematic space, the space of n z's. I know I'm beating a dead horse, but I just want you to get it. Like, that's it. Like, so what we're saying is that it's not like some boundary of some space and some metric and some time and locality. Our space is the space of n z's. It's a 4 by n matrix. And somehow we have to find a question, the space of 4 by n matrices that gives us all the miracles of n equals 4 super Yang-Mills and locality and unitarity and all the rest of it, okay? But one big clue is whatever the heck this question is, has to say that even though it's fundamentally about z's, somehow it has to care about this ii plus 1, jj plus 1 business. This ii plus 1, jj plus 1 has got to be special. The only pole should involve ii plus 1, jj plus 1. Okay? That's, in particular, the only singularities, the only poles should be of the form ii plus 1, jj plus 1. And so let's see here. What do we have? This is ii plus 1, jj plus 1. Good. Okay? This is ii plus 1, jj plus 1. Oh, still good. Okay? This is ii plus 1, not good. Because this is at n equals 6, so it's 5, 6, 1. There's a 6 in between. That's no good. That's a spurious pole, right? This is I plus 1, JJ plus 1. That's good. This is not good. And here too, not good, good, not good, good, good. Not good, 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 not good, good, right? So we see that every term in BCFW, every term has 3 good poles and 2 unphysical ones, 2 spurious poles. Now, probably Jake emphasized this already, but we'll just say it again in this language. We see the building blocks here, they don't care about space-time locality. They have poles in them that just do not correspond to anything that we can think of as a local space-time process. By the way, if you go back to the original on-shell diagrams, this makes a lot of sense. Because what are on-shell diagrams doing? They're gluing together 3-particle amplitudes, on-shell amplitudes. And gluing together 3-particle on-shell amplitudes means that you're not thinking about points meeting at a point in space-time, but you're averaging over everywhere that they can be on a null ray relative to each other. Okay, so that's why it's totally unobvious that they should look local. And in fact, they don't look local. They're not local things. On-shell diagrams are not local space-time processes. They involve averaging things over entire light cones, where the points can get arbitrarily far separated from each other in light cones. Whereas when we talk about ordinary space-time process and Feynman diagrams, precisely because we have off-shell intermediate points, precisely so we can talk about points, right? Rather than everything being localized on shell, which only gives you things that are localized on full light cones. Okay, so, but of course we see that there's hope, because this spurious pole 3451 shows up here, and it also shows up there as 1345, same as 3451. And that's what happens in BCFW, is that the spurious poles kind of cancel in pairs in this example, and the full answer does not depend on them. All right? But this is our first kind of invitation to think. I mean, that we're looking for some kind of structure, some kind of object, something that, you know, will make formulas like this come out in some reasonable way, but it'll be obvious ahead of time why it doesn't depend on 1, why we only see II plus 1, JJ plus 1. Okay, so this is the kind of thing that we're after. All right. So, and that's what the story of the amplituhedron is all about. Okay? So one way of saying what's going on is that you can think of, for example, BCFW as giving you a whole collection of terms. Each term comes from some cell of the Grassmannian, either of the original Grassmannian or under this map of the momentum twister Grassmannian, okay? But in the end, you get a whole collection of objects. Each one is coming from somewhere in the Grassmannian, okay? But we don't know why we have to add them up in this particular way to get the answer, right? Only our desire to make the answer compatible with locality and unitarity tells us that we have to add them up in that particular way. But we don't otherwise know why we're adding them up in that particular way. So that was the sort of frustration, was that you could come all this way with all these remarkable things about the on-shell diagrams and the Grassmannian and all these things that seem like very close to a very different way of thinking about things, but you're still tethered by a longer and longer rope, but still tethered to ordinary quantum field theory by locality and unitarity, right? So what's needed is to sort of cut the rope and to just find some ab initio question that whose answer by itself gives you something, and then sort of read back out that it can be interpreted in this way. All right, so I want to give you, I want to tell you something about what that answer looks like already in this example, but maybe we could pause to see if there are any questions. I think we're 10 minutes from when we turn into a pumpkin at midnight, right? So, so maybe this is a good time to ask for questions and see if I can leave you hanging so that, yes?
Sorry, I missed why were some of the... Sorry, I missed why did, for example, like 1, 3, 4, 5 not work, but 3, 4, 5, 6
it's
work.
all the things that look like I plus 1, J plus 1.
Oh, okay.
Okay? All the things that look like consecutive pairs, because it's those consecutive pairs that correspond to xi minus xj squared that correspond to physical poles.
Gotcha. Okay. Thank you.
And you see, this is one of the hallmarks of BCFW. At 5 points, 3, 4, 5, 1 is a perfectly local thing, right? That is the form I plus 1, JJ plus 1. It's a hallmark of BCFW that after BCFW shifts, the things that were physical poles before become spurious poles afterwards, okay? So something that was perfectly physical for 5 points all of a sudden becomes spurious at 6. Okay?
Yeah, Nima.
Yes.
So it's not clear to me why. I mean, what is BCFW in this? In the sense that the way I understand BCFW is some legs are shifted.
Sorry?
Some legs, some external legs.
That's right,
are
yeah.
shifted.
So I didn't tell you how we got to this point. I'm just
Yeah.
telling you this is what the answer ends up looking like, okay?
I see.
We could take, you just have to take this on faith a little bit, but it's not crazy that it should have something picked special, because you do make 2 legs special when you do BCFW, okay? There's actually a way of describing what BCFW is purely in momentum twisters, but that would take me a little long to explain. So take this much on faith, okay? That if you just translate ordinary BCFW and you just translate it into what's going on in momentum twisters, you get this nice formula in terms of R invariance. Okay?
Also, sometimes in BCFW we have pole at infinity and sometimes we don't.
Right. These are all situations where there's no poles at infinity. Okay. And actually, one of the nice things did Jake talk about super BCFW? Well, I mean that's one of the really nice things about the supersymmetric version of BCFW is that you don't have to worry about who you shift. Okay. There's only one supersymmetric way of doing the shift, and there's never any poles at infinity. In fact, the dual conformal symmetry gives you a very nice understanding for why there couldn't have been any poles at infinity. That's a symmetry explanation for why there's no poles at infinity, because infinite momentum is not anywhere special. You see in this picture, if you have in the dual space, the point at infinity is just any other point. So you can't have a singularity at a random point at infinity. If you did, it would break the dual conformal symmetry. So that's it's not clear what the chicken and what the egg is here, but the absence of poles at infinity in BCFW is intimately related to the dual conformal invariance.
Okay, thank you.
Any other questions?
Yeah. So when you drew the dual geometry in twistor space,
Yes.
you drew it in such a way that made it look like it's not a positive geometry in twistor space.
Oh no, it's not at all. I mean, the picture of the lines is not at all, because it's not even. I mean, there's no notion of any interior. We'll come to that stuff later. But just drawing these lines, I just have a line, another line, another line, another line. I just have a collection of lines.
And so could you set up your problem such that you got both a positive geometry in your kinematic space-time and in twistor space?
Yes, very much so. That's what the kinematic picture of the association will end up, of the amplitude will end up being.
Okay.
Yes. Yeah. This is a super amplitude. So again, this is a very important point. So if we could talk, I assume that Jake had explained about super amplitudes, but if not, these are all super amplitude, and so the helicity is taken care of. Okay, everything is in the super part. Everything is in the dependence on these etas. That's why we didn't have to put any plus minuses anywhere. And yeah, the super BCFW is a really cool thing that you don't have to worry about who you shift and so on.
So when you did the first integral with the C matrix,
yes.
I guess I didn't fully understand in that part, why is it relevant? Like, why do we need to have Suzy to make it work?
That's a great question. And it has a very beautiful answer that, has a very beautiful answer, but let me give you a 30-second. Let me tell you what the answer is about, okay? So, and I won't do details, but you can actually work out the details pretty easily. Remember, we said that I want a delta function that enforces that C contains lambda, and a delta function that says C is orthogonal to lambda tilde. So far, we don't need Suzy for anything, okay? And I want to say, and I want to integrate over some measure on the Grassmannian. So this is, I want a K-plane, so I want to integrate over some measure on the Grassmannian of something, right? Of these delta functions. And it almost looks perfect, except those delta functions are not exactly a property of the k-plane, because those delta functions are not actually invariant under the GL1 part of the GLK transformations. Okay? If you do the SLK transformations, those delta functions are preserved. But if you do the GL1, just the rescaling of the entire matrix, you see those product of delta functions just pick up a Jacobian factor.
Oh.
So even though you thought geometrically you were doing something that was about a k-plane, you're not quite, because those delta functions pick up some weight under the rescaling. And that's what the SUSY part exactly is there to cancel. That's its only purpose in life. And that's why you need Grassmann variables, because you need something that under the Jacobian just goes upstairs rather than downstairs and kills it. And that's the entire purpose. In fact, you could totally motivate the introduction of SUSY just from that. You want to make this picture that appears to be about k-planes really about k-planes. And that means making it really invariant into the GL1. And that forces the introduction of the etas.
Okay, thank you.
Yes?
Yeah, I just want to follow up on her question with Jake was stressing that the SUSY delta function can be replaced by any theory-dependent numerator type thing. So these numerators.
All you need is some object that has the correct weights to make up for the.
That's what I want to know. So they're just
right.
constrained to have this very.
All it needs is something that has weight minus 4k.
Is there any other constraints or?
No.
Oh, I see. Yeah. He always wrote it to. Okay.
Yeah, and in fact, if you take a particular component to the amplitudes, that's exactly what it's doing, right? If you take a particular component out of those deltas, you just get some power of a minor of the C matrix that exactly makes up for the weight.
Okay, great.
Okay. And what's nice about SUSY is that it does it in a way that's totally permutation invariant between all the particles, just the same way as the. Another way of saying it you can think of as a SUSY is just a generating function for all the possible things that you could do, right? Simply made out of the minors of the matrix.
So a short break?
Yeah, about a short break, and I won't. Yeah, again, if you want to go. Although I left you at a kind of exciting point, so.
Okay.
So
a short break. There is still some junk food.
Okay, great. Yeah. There's junk food. All right, excellent. I do need to go to the bathroom though.
Yes.
Although I should not take this with me to the bathroom. Yes.
Please. Straight and yeah. And,